Hello and welcome to EGN3443, Probability and Statistics for Engineers. This is Module 3. We're getting into some meat. We're getting into some meat today. Actually, we're starting into the real stuff. We're starting with probability. Probability is a good thing. Understanding probability is important because to understand probability distributions and predictions made with probability, you got to understand the concepts, the basic concepts of probability. So we're going to start talking about these basic concepts. First, what is probability? Well, as you have probably figured out, many things have a likelihood of happening. Not 100%, not 0%, but somewhere in the middle. So we're really just trying to measure these probabilities. How certain are we that something's actually going to occur? Now, basically everything in statistics deals a little bit with the probability side of it. Statistics is a mathematical discipline, but most of statistics deals with probability. And probability isn't really that complex. We can make it complex, and it does get complex, but but it isn't that hard. It's, will something happen, and what's the likelihood of this thing happening? All right, now let's get into it. First, there's some fundamental axioms, and here's the reality is, if this isn't common sense, you're in the wrong place. First, probabilities are not negative. There is no such thing as a negative probability. In fact, if you think about it, it is actually kind of an interesting concept. The likelihood of this occurring is really not just zero. Things that have actually occurred should be taken away. Probability pulls things that have occurred and says, okay, no, you didn't. Okay, that makes... So, now, on the other side of the coin, so to speak, probabilities, okay, samples, it all has to add up to 1. 100% is the biggest probability that something can actually occur. But the entire sample space of all the different likely events has to add up to 100% or 1. And for mutually exclusive events A and B, the probability of A and B is the probability of A plus the probability of B. Yeah. And these have been proven. Are you need to worry about this stuff? No, it's going to probably be common sense I'm hoping. I'm not going to say hoping for everybody in this class. So, how do you calculate these probabilities? And I'm talking about probabilities. I like to throw dice up here because dice and cards are my real two favorites for probability things. I love to play cards and work out probabilities. So how do you do this? You identify the sample space, you look at what are the outcomes that are favorable, and then you apply the formula to figure out what it is. And many of these are pretty much straightforward. Now, that's assuming some specific things. We're going to talk about those specific things that have to be assumed in this simple calculation. Okay, but because things can interact and you can try things multiple times, and there's multiple things doing whatever it is that you're calculating the probability of, it does get a little bit more complicated. All right, so first thing we want to talk about is the sample space. So an event is something that occurs. And that event will have a probability when it occurs of different outcomes. So if the event were flipping a coin, there's really two different outcomes. There is a infinitesimal probability that the thing's going to land on its edge. Yes, that is there, but we kind of ignore things that are really, really, really small. So if you were to suppose to define the sample space of tossing 3 coins, what are all the different outcomes that could potentially occur? Well, if you look at it simple, I mean, the first coin is going to either be heads or tails. And the second coin is either going to be heads or tails. And the third coin is going to be heads or tails. But when you put all that together, the sample space gets pretty small because the first one can be heads, the second one can be heads, the third one can be heads. Or the other way around, tails, tails, tails. Or heads, heads, tails. Or heads, tail, heads. Or tail, head, head. Or tail, tail, head. So the sample space, and of course, in this specific scenario, is these different possibilities that are actually shown, that I've shown you right here. This is a simple example because we're really just dealing with something that has two possible outcomes. If you did the same thing with 3 different dice, this is going to get a lot bigger because now you've got for each of those 6 potential outcomes for each of the individuals. So a little bit higher level of complexity as you move to more potential outcomes. Now, events. We need to understand events. Okay, we just dealt with the simple event, a specific single outcome that can occur. However, you can take simple events and you can mix and match them. So now you've got combinations, compound events, of different simple events that can occur, and those will have specific probabilities. Okay, then you have complementary events, which is really kind of important. Complementary events are they basically saying, okay, here's the outcomes in this specific scenario, here's the complement, the other side of this. And then there's different ways of looking at the events where events actually intersect. So joint events. Again, these are going to be more by looking at specific examples. You can say, well, if I flip a coin and it comes up heads, it didn't come up tails. Okay? In fact, they're mutually exclusive. Same thing with the dice. And I'm going to give you some examples as we move. I'm going to wait because I've got stuff like this later in this module, and I'll wait until we talk about those there. So when we're dealing with the multiple events, and this is why I was waiting, because you've got the union of events. These, if you've got event A and event B, and they can have their probabilities of each, the union is, hey, did it occur in A, did it occur in B, or did it occur in A and B? It can occur in both. Okay, but if it occurs in either one of them, you have the union. I don't think this is too complex for anybody. The intersection is, did it occur in A and did it occur in B? And then the complement, which is fairly straightforward. What's not occurred in the outcomes that did not occur in A, or the outcomes that did not occur in B. So you can add them all together. You can figure out from different combinations what different probabilities are based on unions, intersections, and complements, because that's kind of, you know, what's the possibility of rolling a dice to a 2 and flipping a coin to a heads. Okay. Multiple events, you can, and I'm going to let you figure these out because they're really not that hard. Okay, by the way, that last one, you should have said, okay, he said, what's the possibility of this occurring and this occurring? What is that? And intersection. Okay. Now, another one, sorry, I jumped, okay, I'll make sure I didn't miss the slide that I was trying to go to. The mutually exclusive event. And a lot of people have issues with mutually exclusive events, but it's a very simple example. If I've got a deck of cards, or if I can't, if I roll a dice, I can't roll a 1 and a 2 on the same dice simultaneously. They are mutually exclusive. They can't occur at the same time. I can't, if I'm drawing a single card from a deck of cards. I like to use deck of cards because as you pull from the deck of cards, you actually remove that individual probability of that card from the deck as you go. That's why I like using cards for this, because it does have a level of complexity to it. But you can't pull, okay, card A, you can't get a queen and an ace in the single pull. Well, you could pull 2 cards, but that's not the same thing as pulling a single card. It violates the premise of the initial premise. Okay, they are mutually exclusive. Independent is really going to be so incredibly important to you. Okay, and the reason is many, when we're dealing with independent events when we're talking about rolling a dice or flipping a coin, it's pretty simple. If you flip a coin and you get a value, and then you flip the coin again and you get a value, the first flip doesn't affect the second flip. If you roll the dice, the first flip doesn't affect the second flip. Okay. However, you're dealing with a deck of cards. You pull one card out of the deck and you look at it, unless you stick that card back in the deck of cards, it now changes the outcome of everything else that's in that deck of cards. There's not a level of independence there. And that this is great and easy with decks of cards and flips. I mean, if you flipped a coin and after you flip it, let's say to heads, you remove all the heads from all the coins, well, guess what? They're no longer independent. That's the same thing as you dealt with a deck of cards. Again, I don't think anybody is struggling with this concept. I'm hoping not so. So when you look, and this is a common mistake, mutually exclusive and independent events. I've heard it's like, well, mutually exclusive means that it has to be independent. No. In fact, kind of just the opposite there. Okay. Yes, a specific individual event that has mutual exclusivity. In other words, you can't roll heads, you can't flip a head and then and a tail at the same time. They are mutually exclusive. And flipping a coin multiple times is independent. Each flip is independent. But flipping a coin one time, okay, getting the heads, well, getting the tails on the same flip, if they're mutually exclusive, they're completely dependent. Getting a heads means you're not getting a tail. It's 100% dependent upon the actual outcome of the event. Okay? They're not the same thing. So kind of get that through your head. They are independent of each other. All right, so let's go into some more stuff there. This is terminology. It should make sense. Now, conditional probabilities. This is where we get into some fun. Some real fun. Because when we talk about conditional probabilities, something has occurred, but we're looking at the probability of occurrence given that another event has actually occurred. It's a nice easy formula for that. When we're dealing with many sequential events, or we're dealing with diagnostics, which is one of the fields that you do a lot of conditional probabilities. If something breaks on your car, what's the probability of something else breaking? Is it? Is there a condition that goes there? There may or may not be. Which is why you have to really look at these. Now, when we get into Bayes, which is the next slide, by the way, when we get into Bayes, you can kind of see this. And I'm going to give you some advice about how to look at these things that will really help you out better than I can explain it. Well, I could probably just repeat what I know from my explanation here, but I'm going to give you a more entertaining approach here. All right, so Bayes' theorem. Bayes' theorem. You don't need to memorize the equation for Bayes' theorem. You need to understand Bayes' theorem. And it's so important, if you already understand Bayes' theorem, if you understand, okay, how these conditional probabilities work together, you're good to go. If you don't, okay, the best way to get that understanding and the real application is looking at probability differences between samples and populations and when you're doing something specific like testing. And that's one of the biggest the classic example of Bayes' theorem. What you should do is go to YouTube and Google or YouTube, do a search for the Bayesian trap available from Veritasium. It is excellent. It's a great explanation of it. And the reason I'm pointing you at this one is because it's not only an excellent explanation, it is also entertaining. Okay, actually, I find most of the videos from Kyrgyzstan and Veritasium to be highly entertaining. If you don't know these and you're a person who likes to learn and know and have knowledge, there's a whole bunch, by the way. I mean, it's not the only two, but my two favorite learning videos from YouTube, because they're completely free and they're entertaining and they're informative, is Veritasium and Kyrgyzstan. There's also a few others, other people who do these types of things, and I'm going to probably get into doing this because I may not be as entertaining as they are, but you know what? I am at heart, I like to teach people. So the classic example that you're going to see in the example that you look at Veritasium is the medical testing example. And I'm not going to get into it other than to say that if you have a population occurrence of some specific disease that has a probability, and you go get a test that has a specific probability of, I mean, if you're positive, it has a probability of actually correctly testing you. And you look at that test, you would think that, oh, if I have a test that has, it is 90% accurate, then if it tells me I've got a disease, that means there's a 90% chance I have the disease. Is that actually true? Okay. Maybe just a piece of advice. You're going to go out and watch some more stuff on this. I want you. This is homework. But maybe you might want to get a second opinion. Just saying. But you need to understand why that second opinion is so important. All right. Law of total probability. Here's the issue. And we're living in a statistical world where you're doing this. We don't necessarily have the population in every single occurrence of something. Now, we may have the population with a deck of cards. There's only 52. You may have a population with the roll of a dice. There's only 6. Flipping a coin, there's only 2. But not always. We're dealing with the sample space, which may be a sample. But the reality is, if you can look at the sample space and you can partition it completely, you can calculate the probability of any of the events. Okay? Because you can follow the path of each individual probability. Well, what do I mean by the path of each probability? Well, this whole law of total probability, just to give you a point, the reason it is extremely useful is because many probability problems are extremely complex. And to reduce that level of complexity, what you really want to do is break it down into more simple components. So, law of total probability allows you to do that. So let's kind of get into this concept of a probability tree that will help you out here. 2 examples here, but what you're going to look at is, here's some events that can occur. And each event has a finite set of outcomes, which means you can create a tree from that finite set of outcomes. Now, as you do this by hand, that tree can get really, really big. Okay. But we don't always do this by hand. We do this with a computer. And then you look at all the different branches of that tree, because a tree is going to give you all the potential outcomes of something. And you go through every single branch that gets you to the outcome that is the specific outcome that you're interested in. That is actually say the probability of success or failure, because you often use probabilities of both. then you know you can actually determine the overall total probability because you're looking at the paths that lead to a specific end state. What is that final outcome that you've got? Now, that gets us into something else because guess what? Sometimes even all those potential probabilities are insanely large and complex. But we have a way of dealing with that too. So in practice, we kind of deal with this concept of which is a direct application of this, is reliability. Now, this is kind of lead us into the other modules where we start talking about the distribution, the function that describes a specific reliability or a specific probability. This specific case is the reliability function, which deals with failure rates. How often, what's the period, and we've got multiple ways of measuring this, but what's the period that is necessary, that occurs between failures. But the reliability function basically wants to know, is something going to survive in a successful state without failing? Okay. So don't overthink this. It is what it says it is. Something is reliable if it doesn't fail. It has a probability of not failing, which it also has a probability of failing. And knowing that those are mutually exclusive events, it can't fail or not fail. I mean, you can't do both at the same time. You can build a reliability function. And that reliability function often follows specific mathematical patterns. And again, relatively simple when you're dealing with a single type of component with a single type of failure. And unfortunately, as I move on to this next slide, that isn't necessarily what happens, because oftentimes you've got individual components that have each of these probabilities associated with them that either are in parallel, but we're going to talk about series first. When the components are series, and this means mathematically in series, it doesn't mean that you've got an actual circuit in series, but a circuit in series will have this. If you have a bunch of resistors in series and one of the resistors fails, the system fails. That's simple. Same thing in you're talking about probability. If one of them fails, the system fails. Okay? In parallel, as long as you got one component working, it works. Now, it may not work as well as it did with every component, but it's still functional. All right, you're going to have systems that have components that are mathematically, statistically, in dealing with failure of the system, that are combinations of series and parallel. And as you can see, you can come up, if you've done circuit analysis, you know perfectly well that these can get relatively complex. Luckily, there are known mathematical distributions which most of these systems follow. So if we know what system they follow, we can actually use these distributions. That's kind of leading us into the next module. Exponential, Weibull, and normal. I should have put those in completely different order. It should be normal, Weibull, and then exponential, because we use normal a lot. We use Weibull a lot. We use exponential we use normal more than Weibull more than exponential. Okay, well, the point being that we have a mathematical formulation for predictive abilities of large samples that deal with a lot of probabilities and put them together, because these all follow patterns. Okay? And when it gets really complex, we've got the Monte Carlo simulation. So what is a Monte Carlo simulation? Well, if we know the individual patterns of individual components in a complex system, we can simulate that system. Now, you can simulate the system on paper, but and actually, if you've ever played Dungeons and Dragons, real Dungeons and Dragons with a dungeon master and a multi-sided die, you've done Monte Carlo simulations. You've actually done this because there's a lot of different potential outcomes. When we deal with this and we're not playing Dungeons and Dragons and we're not doing it on paper, we can use a computer to simulate each of the individual components, put all of those individual components in their parallel and series, or however they actually interact with each other, and create an overall system for the entire type of event. And that gets back to my good old, if you've heard me talk about my dissertation used Monte Carlo analysis to deal with extremely complex riverine systems. And in those extreme systems, I developed a Monte Carlo simulation that could simulate the overall probability of things occurring based on what was occurring at other locations and knowing the distribution at other locations. And then I was able to use that to come up with an overall mathematical scenario for the entire system. So I didn't have to do a Monte Carlo every single time, which is kind of a field of mathematics. But that gets beyond what we're talking about in this class. If you know how the individual components behave, regardless of the fact that they may be in some sort of complex configuration, we can figure out the reliability of the system by simply simulating the system and then looking what happens. You can run thousands and thousands of trials, tens of thousands of trials, hundreds of thousands of trials, millions of trials, and then look at the overall system performance. So, what do we know from this? What have you learned? Hopefully, this is just going to whip your appetite. The core concepts of probability and sample space, how to solve probability problems, looking at the concept of, one of the big ones was looking at Bayes, understanding Bayes, looking at, hopefully you watched the video, and if you still don't understand Bayes, I will help you, and then the ability to use Python R as part of this problem-solving approach to get to whatever it is that you're actually looking for. So, conceptually, the concepts are important. The details, you're going to use those concepts to figure out the details. And guess what? I'm right here to help you through everything. So that's it for Module 3. We're going to be moving on into some of the true meat as we start going into distributions next. Signing out, Dr. Eaglin.